In May of 1921, at the Smithsonian Institute's Museum of Natural History in Washington, D.C., two great and eminent scientists, Harlow Shapley and Heber Curtis, participated in what was to be called the Great Debate. The issue? The size and structure of the universe. In particular, the size, uniqueness, and our location within the galaxy. Shapley believed that our galaxy was huge, one of a kind, and that we lived close to the center. Curtis believed that our galaxy was small, one of many millions of such galaxies, and that we lived nowhere near the center. It turns out that both men were wrong and both men were right, just about different things. Shapley thought that the galaxy was shaped like a uniform lens, 300,000 light years in diameter and 50,000 light years thick. But Curtis thought that the numbers were 1/10 that size, just 30,000 light years in diameter and 5,000 light years thick. Actually, our galaxy is a very flat spiral. It's over 100,000 light years in diameter, but it's only just about 1,000 light years thick. So Shapley overestimated the size of our galaxy by a factor of 2, but Curtis underestimated it by a factor of 5, so Shapley won that point pretty well. On the other hand, our galaxy is not one of a kind. It's nowhere near unique. And we don't live close to the center, so Curtis won on those 2 points. What drove this disagreement? How could two great and well-respected scientists come to such vastly different conclusions by looking at the same data? You see, 36 years earlier, in 1885, a new star appeared in M31, the Great Nebula in Andromeda. It was just barely visible to the naked eye, but in a telescope it appeared to rival the brightness of the nebula itself. Now, one of the issues in this debate was about the nature of the Andromeda Nebula and all the spiral nebulas, of which apparently there were millions. Curtis thought that the Andromeda Nebula was a galaxy like our own Milky Way, relatively small and pretty close by. Shapley thought that the nebula was a bunch of dust and gas inside our own galaxy. In either case, however, the 1885 nova would have been a bright but relatively normal nova. But if our galaxy was 300,000 light years in diameter, as Shapley thought it was, and if Andromeda were a galaxy too, just like ours, well, that would mean that it was millions of light years away, and that nova would have had to have been brighter than 1 billion suns. Neither man wanted to accept that. And so Curtis made our galaxy very small so that the Andromeda galaxy could likewise be small and near, whereas Shapley brought the Andromeda Nebula inside our own galaxy. To draw these different conclusions from the same evidence, both men had to selectively reject some of that evidence. For example, Shapley used Henrietta Leavitt's period luminosity relationship to calculate the distance to Cepheid variables in many of the globular clusters around the sky. And he got the distances just about right, too. Some of those distances were remarkably large. Their arrangement in space gave them a diameter of 300,000 light years. And so Shapley thought they were internal to our galaxy, and so he gave our galaxy a diameter of about that size. But Curtis rejected the period luminosity relationship on the grounds that it hadn't been well tested or calibrated. He convinced himself that it could be as much as a whole order of magnitude off. By the same token, Curtis argued that the spiral nebula like M31 and Andromeda could not be part of our galaxy because, One, they weren't distributed across the sky with any shape that resembled our galaxy. In fact, the distribution was nearly exactly the opposite. And two, their radial velocities were more than 10 times greater than any other object in the sky. But Shapley just ignored this evidence, preferring to rely instead on certain photometric observations that seemed to suggest that the spiral nebula could not be systems of stars. Now, I'm oversimplifying the case. The arguments made by these two men were actually very compelling. These were two very intelligent, highly experienced, well-regarded scientists. But the point remains that neither man could imagine a stellar explosion so vast that it would outshine every star in the Milky Way. And so both men found convenient ways to put M31 at a distance that would make that 1885 supernova seem more normal. And in both cases, those convenient ways were to brush aside the data that didn't fit with their favorite model. The moral of this story is that scientists are human. They can be both right and wrong at the same time. Arthur C. Clarke said it well. He said, "When an elderly and distinguished scientist says that something is possible, he is almost certainly right. But if he says something's impossible, he is very probably wrong." I think a reasonable corollary to that is that when a scientist says that a scientific conclusion is debatable, he's almost certainly right. But if he says that the science is settled, he's very probably wrong.